Hi, welcome to the second video in a series on introductory data science with R. I'm Dave Langer, your host. I want to start this video briefly with some housekeeping items just to catch up on some things that I probably should have elaborated more on the first video but did not, as well as provide some pointers for folks that may be interested. So first, I want to point out that all of the code that you see in the video will be uploaded to my GitHub and will be publicly available for anybody who wants to look at it. Just note, and I hate to mention this because it's not particularly interesting, but necessary, that the code is licensed under Apache 2.0, and that's just mainly for coverage for myself, my employer, and for you. Okay, so after each video I will upload a new file that corresponds to each video in the series. Essentially it's all the same code, but it iteratively gets more and more code added to the file as we cover more and more topics. Okay, so this is something I mentioned last time, but I also want to reiterate this point quite clearly. I am not an R expert, and to be honest with you, I don't purport to be one, nor arguably will I ever be one per se, not in the spirit of Hadley Wickham, if you know who Hadley is. I do want to emphasize this because what you'll see in these videos is that I will tend to illustrate multiple ways of doing things. As with most programming languages, you can do the same thing multiple different ways in R. To be completely honest, I've actually found that there are more options in R than probably most other languages I've used personally. And I also want to emphasize is that the code that I will present, by my own admission, is not always going to be optimal R code. For example, if you were an R expert, you may cringe at some of the things that I do and talk about. And I think that's okay for three reasons. The first one being I disclaim that I'm not an R expert, so that's kind of my air cover. Second, I'm not writing in these series production code. What we're doing here and what we're seeing here is very much a early stage iterative analytical process in the overall data science / predictive modeling / data mining project lifecycle, and this code really isn't production code. Now there may be firms that put R code in production, but generally speaking, to my knowledge, most of the time what you see is R is used for iterative prototyping early in the project cycle, and then something else is used if the system is taken or the solution is taken to production, whether that's Java, C#, Python, whatever it may be. Closely related to that is that I am not in the business or in the hobby of writing R packages. Now, if I was to start writing some R packages, then I would really be concerned with writing good optimal R code. However, that's not me. There are far better people in the R community at doing that than myself. I just stand on the shoulders of giants and kind of hack my way through it. And I think that's okay, if no other reason than because if your customers or your business partners or anything like mine, they don't really care about code purity. What they care about typically is cycle time. How fast can you get something done? Is it relatively good enough for their aim? Does it give them enough business value for the effort? That's typically what they care about. So enough on the R code. Please don't send me any nasty grams. I understand that I'm not an R expert, so your mileage may vary regarding the quality of the code that you see. However, hopefully the results that you get will be interesting. Okay, lastly, some folks may be wondering, hey, Dave, this is a introductory series on data science, and to my eye, you spent an hour and 20 minutes last time talking about stuff, and I didn't see anything that looked like data science to me. Specifically, I didn't see you build any predictive models. What's up with that? So the answer is, quite frankly, this is something I had to learn personally the hard way. When I first started, I wanted to build models and do submissions to Kaggle and predict things. And to be honest with you, I didn't do so hot in the beginning, to be quite frank. I had to learn the hard way that this is true. Algorithms are great, but nothing beats knowing your data. And how I typify this when I talk to folks these days is that if you do Kaggle competitions, invariably what you'll see is new folks coming in, which is great. I mean, that's kind of the point of Kaggle, is to broaden the data science community in general. And you'll see folks that will say, hey, I'm new to machine learning, or I'm new to Kaggle. What is the best model I should use? And typically what the response is from the old hands on the forums who predominantly know what they're doing, for from all intents that you can tell from the website, essentially say, yes, algorithms are great, but nothing beats knowing your data. Do the data analysis up front. There's a famous quote from a scientist from Google, I forget the gentleman's name, who essentially says that more data always trumps better algorithms. It's essentially the same idea, which says even in the small data world, quote unquote, knowing your data and being able to engineer good features is going to be better than algorithms. That's not to say that picking the right algorithm is not important. It certainly is. Tuning the algorithm is not important, because it certainly is. However, all things being equal, better feature engineering tends to trump algorithms and algorithm tuning. Now, this next point is something I also learned very hard myself in my own early explorations into data science, which is that data analysis will save you a lot of time. Unless you're dealing with very simple models, something like a linear regression algorithm, training a model takes a lot of time. And the more complicated the model, the more interesting the problem set, the larger your data set, the longer it takes. So data analysis is actually an optimization strategy for you as a data scientist. Because in the end, nothing beats the ability to iterate quickly, to try things out, understand how they work, tweak something, engineer a new feature, tune a parameter, what have you. Nothing beats able to do that cycle time. Now, if you can do some data analysis up front and find out stuff that, take a look at your data, find out what's probably predictive, what's not predictive, what features may be interesting, it will save you a lot of time. I cannot stress this enough. And this may sound very existential, but eventually your data will speak to you if you spend enough time with it. I mean, not to say that you'll be a data whisperer in that sort of sense of the popular reality TV shows that you can see on television in the States now. But it is true in my experience. And it usually takes the form of two things. Once you spend enough time with your data and actually get a feel for it, it starts to almost speak to you about what's likely to be predictive and what's not. And we've already seen this in video 1, and we'll go over this again here shortly, about pulling out the title from the name field in the Titanic dataset. It seems to be that's likely to be predictive. If you don't spend any time with the data, you may not have noticed that there seems to be something funky going on with this title thing that's in this name string field in the data. The data will also tend to speak to you regarding new scenarios. The more familiar you get with the data, the more you start to imagine in your mind's eye almost a story around the data. And I find that that's very helpful for feature engineering most particular. And as I mentioned earlier, in the end, algorithms are great, tuning is important, but nothing beats quality feature engineering. And in fact, you can find videos on YouTube of Kagglers who have either won or placed very highly in competitions using relatively simple common algorithms like random forest, for example, but what put them over the top in terms of results was the feature engineering that they did. Okay, enough of the housekeeping. Let's go ahead and close Word down, and let's bring up R. I'm going to go ahead and maximize this for the real estate. So I've already set my session using the GUI here for choosing my working directory, and all I'm going to do is just select all the code from video 1 and just run it to set a baseline for everything we're going to do next. Okay, highlight all that, click run, and you'll see here that you get a bunch of output and all of our plots come up from last time. So to level set us, I want to reiterate where we ended up last time, which is we looked at a bunch of data, did a bunch of exploration, and in the end we thought this title portion of the name string was interesting. Let me scroll up here and we can take a look at some examples. All right, so you can see here, Mr. is a title, Master is a title, and we started to take a look at it and say, there seems to be a correlation here with age and marital status and all that kind of thing based on title. So we did a nice visualization here to say, look, is there anything to this aspect of the data, right? It's the data starting to speak to us. And we said, hey, it looks pretty interesting, right? In general, males don't survive very well, especially in third class, unless they tend to have master as their title, and that seems to be relatively predictive for males. Miss also seems to be relatively predictive versus misses potentially in various scenarios, and we should probably take a look at that a little bit more in depth later, as we actually will take a look at it a little more in depth later, but I just wanted to level set us. So we found that, P class is interesting, as we thought people who live in first class were in first class in the Titanic tend to have better survival rates than those who are in third class. Second class, also, this general rule holds. Generally speaking, P class 2 was more survivable in general than P class 3. And lastly, we also noticed some differences between males and females, right? We supposed, based on this analysis, this idea that's common in the US and probably in Western Europe in general, maybe Australia and New Zealand as well, this idea of women and children first. This is the data speaking to us, a scenario that we may explore even further to help us guide in our feature engineering activities, which is, if people were married, if a married woman was traveling with her husband, was she more likely to survive, less likely to survive? These are things we'll probably take a look at because this data is starting to speak to us about these types of scenarios. Okay. Also, one of the things that we discussed was that potentially title could be used as a proxy for age. In particular, we noticed that master tended to denote male children or boys, and miss denoted definitely female children, girls, but also unmarried women of various ages. So, but we did know there was some correlation, some tie between miss and age, but definitely master was correlated to age. So let's go ahead and turn our attention to actually taking a look at some of those aspects that we just discussed, not the least of which is, let's just take a look at sex real quick. So across the combined data set, we can issue the table command here. And as I mentioned last time, don't hesitate to use the R help system. And here's the help documentation on the table function. But we can see here that, it was predominantly a 2-to-1, almost basically a 2-to-1 split between males to females. And males were far more likely to perish than female passengers were. So this will be interesting later on when we start to get to the modeling aspect, because in general, the models tend to optimize themselves for the data they're presented. And here we're presented with the fact that you got almost a 2-to-1 ratio between males and females, and males were far more likely to perish than females. So you wouldn't be out of the realm of possibility that you may build a predictive model that essentially says, if you're male, you perish, and if you're female, you don't perish. And maybe that's okay, maybe it's not, depending on the application. For the cackle competition, which is measured predominantly on accuracy, that's not going to work for us. We're going to want to get a model that's far more fine-grained than that. And we'll talk more about that later. Okay, and let's go ahead and fire up ggplot 2, because I like to visualize my data. Tables are great, but I tend to like graphics better. The story tends to pop better for me when I see it in a graphical format. Okay, and here we've got the plot, and this is a 3-way relationship between survival rates, as denoted here by colors. This orange color means that the passenger perished, and this turquoise type color means that the passenger survived. And then we broke it out by sex, and then P class. So essentially, wealthier males and females, more middle of the road males and females, and then relatively speaking, poorer males and females. And this is particularly interesting because you'll notice that in general, there's not much difference in survival rates based on this visualization anyway, between females in first and second class. Females in third class is not nearly as good as first and second class, but still far better across the board than males. What's particularly interesting here is that, males in first class had the best survival rates easily by looking at the proportions here on this bar graph, this histogram. And surprisingly, in second class, they actually got quite a bit worse. And then maybe if you look at proportionally, maybe second class for males isn't necessarily super better than third class, which is potentially interesting. Now, this plot is very much an exploration because, as we saw from the previous plot with title, these designations of male and female are pretty coarse-grained because now we know we have master, we have miss, we have Mrs., and we have Mr., and within miss we probably think there's further breakdown between female children, girls, and then unmarried adult women, which would also have the miss designation, but may have different survival rates. So this is pretty coarse-grained, but still not, it's still worthy of a quick plot just to take a look at it. But there's nothing here basically that would say that would invalidate this plot. In fact, I would say in general, this just confirms that this breakdown is more interesting. That titles, we're on the right track with title. Okay. Enough about the sex of folks. Let's take a look at age now. As we talked about before, we've got what we think is a proxy for age in the title variable, but let's just drill in on that a little bit. So I've used the summary command here, and of course, don't hesitate to use the help system here. Oops, let me spell that correctly. Here's the help documentation for the summary function. But in general, what would you typically use summary for, at least what I typically use summary for, is for numeric variables. And what it does is it gives you some nice summary statistics about a variable. As we know, age is it's a floating point decimal value, as you can see here. And what summary gives us essentially is a bunch of summary statistics about it. So this is the minimum value, the max value, the median and mean values, and the first quartile and the third quartile. Also, very helpfully, it gives us the count of the missing data, the nulls. So the first thing that jumps out at me here is this value. So we have 1,309, as you can see up here, in the data combined variable. We have 1,309 total observations, and 263 of those for the age variable are missing. That's quite a lot. That's what, one in 5? About 1 in 5, a little more than 1 in 5, a little less than 1 in 5. That's kind of important. Missing values are a big deal, and handling missing values is also difficult to address. So you have a number of options when dealing with missing values. One is typically so hypothetically in the scientific world, one way to address missing values is to actually go collect them. So you can imagine if you're conducting a scientific experiment, you could send out a scientist or a graduate student or a lab assistant or something like that and just try and collect the missing values. And maybe that's realistic for a scientific type of situation. But generally speaking, when you're doing data science in the business world, usually it's either cost prohibitive or basically just not feasible to collect missing values. That could be for any number of reasons. That's just my experience. Maybe your business is different, but in my experience, that is usually the case. So given that, the realistic options in my experience have been you can either try to infer a value. So for example, you may just replace an empty value with a median or a mean for the class of variables in question. So for example, we may go and find out what the median value for adult males in our data set here is for the Titanic passengers and just replace any missing values for folks with the title of Mr. with that median value. It's a reasonable strategy. It's actually done. It tends to make me a little bit nervous, but it is something that can be done if necessary. Another option is known as imputation, or literally what you'll do is you'll create a predictive model on your data to predict, using the data that isn't missing, what the value of the missing data should be. So for example, you could train let's say a linear regression model for the entire data set and then use that linear regression model to predict the missing values. Now, typically what you would do is you could use the entire data set for that, or just the training portion of the data set for that, and you would just leave off in both cases the label and use all of the rest of the variables as input and leave the age value out, and then build a model that to predict age on the rest of them. So there's been lots of academic research that shows that imputation actually works pretty well. For example, a very common method is to use k-means clustering to try and k nearest neighbors clustering, to use that to impute essentially what that value should be. So that's another option. Lastly, and this is the option that I try to use wherever possible, is try to find a proxy or some other value that mimics essentially the variable in question, so you don't need to worry about it. As is the case with our title variable that we engineered out of the name strings for each passenger. We're showing our analysis, our initial analysis, our gut feel is that there's a strong correlation between title and essentially age insofar as it relates to its predictive strength for survival on the Titanic. So we can explore that a little further, because this is a lot of missing values. I mean, I would not want to try and use imputation on that if at all possible. And we can do this we can even do this real quickly, even further and say, okay, let's see how bad this problem really is. So let's go ahead and look at the train variables and see what the summary is. So what I'm doing here is, and you know what, I should probably just put this in the file so that we'll have it later. So give me a summary, but just give me a summary on the first 891 observations, and give me the age variable. So this will just say, look, I want to do a summary, but I only want to do a summary on the train data right now. So let's take a look at that and see what it says. Okay. So this is some bad juju. Not only do we have a lot of missing values, but more than half of them are in the training data, which means that our missing values are even skewed to the training data, which is an unfortunate situation. This would only, to me, reiterate the need for focusing in on finding some other variables that I could use as a proxy for age and not have to worry about providing values or imputing values, because this is a lot of missing values. So I would worry about the accuracy of the model, the validity of the model on that. Okay. Just to be even more thorough, we're going to go ahead and see a visual plot. And let's use a handy feature here of RStudio, which I can zoom in on. I'm going to get an even bigger view, which is kind of nice. Okay, so what we've got here is a plot, and I should have put a title on there, apologies, showing the breakdown of female by class and male by class, survival rates in general across ages. Okay, so as we can see here, females in first class, very good survival rate. There doesn't seem to be a discernible pattern here. We've just got single blips here. These are, you can see here based on the scale, these are probably pretty close to, it's 1 or 2 passengers maybe. So 1 or 2 passengers perished, and there's really no discernible pattern here. Females in second class, a little bit different. There appears to be a pattern that involves, hey, look, around, this line here corresponds to 25. This is probably 12 and a half and 12 and a half. So what, 12.5 up to 37.5 years of age. Big blip here. And getting older, you get females that perished in second class. So in general, it looks like, hey, you know what? If you're pretty young, if you were a pretty young female in second class, likely based on our training data, you survived, which is an interesting pattern. Females in third class, it's kind of, kind of a pattern here. It looks like it's about, maybe roughly 50-50, 50-50, 50-50, and then it starts to get worse, except for this outlier out here, which could potentially be interesting, but doesn't necessarily denote a pattern per se. It could just be, an odd record. Okay, in males, not surprisingly, let's start with third class because that's really interesting. Third class, pretty sad story here. If you're a male in third class, the older you get, in general, the worse your appears to be the worse your survival rates, especially when you get up in the much older range. Okay, looking at second class. Yep, if you're young, which corresponds to this idea of master, pretty good odds, and then it gets pretty sad after that. And in first class, now this is interesting, that odds aren't so good. They get, they decline quickly for males, even in first class. So this is more potential evidence to this women and children first theory that we've got going on, this story that the data may be trying to tell us. All right. So we've got a hypothesis, we've got a theory, to butcher scientific nomenclature, around this idea of the master title. So let's go ahead and take a closer look at that just to get a better feel for the data. Okay, so first thing I want to do is I want to talk about which. So use the help system, especially when you start out with R. Okay, which. And it's a function that says, hey, I'll tell you which indices are true. So basically it's almost like a where clause if you're familiar with applying SQL to a database table. We're essentially saying here, hey, look, go to the data combined data frame, which we can see here is 1,309 observations of 12 variables. Take a look at the title variable inside of it and check to see if the title variable is equivalent to the string master period. And then tell me which of those observations are true and false. So if we really want to, we can just run this real quick. And you'll see here, cool, this gives me a list of all the various records by index. So this is observation 8, observation 17, observation 51, all the way through observation 1309. And all of these are true. They're saying, look, it meets this condition. So what we're saying is, hey, from the data.combine set, grab me all of these indices because I'm interested in them because they correspond to a title of master. And then assign that to a variable we're going to call boys. And then what I want you to do is then go ahead and do a summary on the age of boys. So I'll just go ahead and run that again. And we can see here, okay, this is pretty interesting. This data seems to confirm our initial hypothesis, which says, look, master is a reasonable proxy, for male children. Because you can see here the max age is 14.5 years old. The min age is 0.33. And also, interestingly, there's only 8 missing values, which is interesting because, as we saw here, in the train set, there's actually a total of 177 missing values in aggregate. So very few of the missing values happen to correspond to records with the title of master. Okay, so master seems to be at this point a very good proxy for male children, which means reflexively, Mr. is a good proxy for adult males, so we could probably not have to worry about the age variable for males in this data set. We can just essentially say, look, we'll use title to indicate male children and Mr. to indicate adult males. Okay, great. So, but we know that Miss is a lot more complicated than that. So let's take a little bit more look at that particular data set. So again, we're going to do the same thing. We're going to use which. We're going to say go through all the data, find those that have a title of Miss, return me back which of those meets that condition, subset the data from the data combined, give me all the variables here because you'll notice after the comma there is nothing, and store that in a variable called misses, and then summarize that data. So we'll go ahead and do that. Okay, now this is where it's particularly, this confirms our suspicion that miss is more complicated because you'll see here that, interestingly, there are 50 missing values. Oh, excuse me. So I said earlier that this was 8 of 177. Actually, that's not true. This is on the combined data set. So this is 8 missing values out of 263 values. Apologies for that. I needed to pause the video for personal weirdness. As I was saying, 8 of the overall 263 missing values are actually for the master record, not 177, because this is over the whole combined data set. My apologies. Similarly, it's 50 missing values for the miss data set. Okay. Now, what this tells us is, as we expected, it's more complicated for the miss records. In particular, what this shows us is that we have a mixture of children. As you can see here, the minimum age is 0.17, which is quite young, and the max is 63. Most definitely not a female child. And the data is certainly seems to be skewed towards the low end of the spectrum. Fully 25% of the records overall are age 15 or less, but they tend to be skewed, to the right end of the distribution, which means that, in general, most of the records who have a title of miss are actually adult women and not necessarily female children. Okay, so we're gonna have to take a look at that later, probably in more detail. But as is my wont, let's go ahead and take a look at this real quickly in ggplot. And you can see here, here's the age distribution for the miss title by P-class, and again, survived. And here we have first class, as our previous plot showed, just based on female age. We've got this, a couple of interesting little blips here. These, based on the scale, looks like it corresponds to one record directly. And you can see here, it looks like one very young female perished in first class and one older female perished in first class. But in general, if you had a title of miss and you were in first class, you had a very, very good chance of survival. Similar story in second class. In third class, the story appears to be a little bit more mixed. As you can see here, for this bar, relatively speaking, area-wise, generally speaking, if you were very young, you were more likely to survive than not, but not nearly as, it's not nearly as pronounced a relationship as you see here in first and second class. And in general, as you get older with the title of miss, your percentage chance of survival gets worse until, you're, see here, probably what, 30 or so or older, and it's pretty bad. Okay. So what this tells me is that, so it's probably behooves me to do some feature engineering at some point later on. I'm not going to do it today in this video, but later on regarding breaking this down. I want to find out, realistically, I want to say, if you have a title of miss, I also want to know, are you a child, right? That is at the low end of the age spectrum, or are you an adult at the high end of the age spectrum? Because it looks like, especially in third class, there's going to be some predictive power there. And given that there's a large number, there's a lot more females in third class than there are in either first or second, that's probably going to help my eventual predictive model I'm going to build to be more accurate. Okay. Excellent. So let's go ahead and just explore that a little bit more here. Okay, so what I've got here is, just to confirm my initial suspicion, I've got some code here that says, look, I'm going to create a variable called misses.alone and say, hey, find me all of the misses, right, because this is the misses up here, that are not traveling with any siblings or spouses and not traveling with any parents or children, right? So this syntax is interesting. Notice that unlike a lot of programming languages use a single ampersand here to do a logical AND. So this says, hey, go through all the misses data records, find those with a sibling spouse record equivalent to 0, and then also find me a parent-child record whose value is 0. and then return me back the indices where both of these things are true simultaneously, give me back all of the variables, and pull that from the main misses data set and cram that into the misses alone variable. Then summarize the age for me, and then give me just the length of which, hey, if all these records of women with the title of Miss that are traveling alone, that is no siblings or spouses and no parents or children, how many of them are less than 14 and a half? And the reason why I picked 14 and a half was that was the max value that we saw here for those records, those male records with title of master, which we assume to be boys, male children. So just want to say, hey, symmetrically, what does that look like? So you can see here that the distribution gets even further skewed to the right in terms of age as opposed to misses all up, right? So this shows the distribution of age for all records, regardless of whether they're traveling alone or with other folks that also have the title of Miss. And you can see here 25% of the records are have an age of 15 or less. In comparison, for those women who are traveling alone and have a title of Miss, fully 25% of them are age 21 or older, and the minimum value is 5. So that what that tells you is that in general, if women are traveling alone, they're probably adult females. And this seems to also confirm this hypothesis, which says, look, okay, how many of these records are actually less than or equal to 14 and a half? And the answer is only 4. So just think, so something to keep in the back of your mind for future feature engineering is that we may do something, a simple rule of thumb that says, look, if you have the designation of Miss and you are traveling alone, we're just going to say that you're an adult female. We will be wrong at this stage a little bit of the time, but not too bad, because you can see here that we have 150 observations in Misses alone, and only 4 of them correspond to a child. So that's a pretty good ratio. That's a reasonable approximation. Now, if we do some feature engineering and we do some more work, we may actually find that we can use better heuristics or better logic for engineering that female adult or female child variable. But at this point, this looks like a reasonable thing to start with for at least determining whether or not a female record with a Miss title is adult or child. Okay. Moving on. Let's take a look at the sibling spouse travel variable, or SIB-SPA, for lack of a better way of pronouncing it. So we'll run our summary function on that, and we get back some relatively interesting information. It says no NAs. That's good, because we don't like missing variables, like we said before, missing values for variables. And this is particularly interesting, is that the minimum value is 0. The 25% of all records are 0. The median is 0, which means half of the records have a value of 0. And the mean is only 0.49889, which, as we know from our metadata that we saw last time, forgive me, let me go ahead and pull up the Kaggle website so we can take a look at that. The SIB-SPA variable is actually the number of sibling spouses aboard, which essentially means, okay, it's an integer. So this tells me that what we've got here is that this variable is heavily skewed to 0. So given that there's only probably a finite number of values that are possible for the SIB-SPA variable. For example, it's unlikely that the number will be 50, because that means you'd be traveling with 49 brothers and sisters and 1 spouse. Excuse me. That's highly unlikely. So it's probably, at most, as we see here, around 8 values possible, because we have a max of 8. We know it's an integer value. Is it possible that we may have 9, 10, 11, or 12? Maybe, but generally speaking, it's going to be a finite number of possible values. So one of the things that would be interesting is to say, look, can we treat this variable not as a numeric, but turn it into a factor, into a categorical variable. I.e., could it be equivalent to a drop-down in a web page, a number of finite values that we can choose from? If we can do that, it allows us to do some interesting visualization techniques. It makes things a little bit easier from a data analysis perspective. So one of the ways we can try to do that is to say, look, find me all the unique values, and then tell me how many there are. So once again, let's take a look at the help system for the unique function. And it does exactly what you would think, extract the unique elements. And we can also do it for length. And gives you the length of the object. So what this says is go to the data.combine variable, or excuse me, the data.combine data frame, grab me the sibspa variable from that data frame, and for all of those values, find out how many are unique, and then just tell me the length of the uniqueness, and that just gives me the count of how many unique values we have. And it comes back and it says 7. I say, okay, well, you know what? That's pretty reasonable. So if across the entire data set, there's only 7 unique values, 0, 1, 2, 5, 8, whatever, for a sibspa variable, so I can turn it into a factor using this code, right? Grab the variable sibspa from the data.combine data frame, transform it into a factor, and then cram it back into the sibspa variable of data.combine. That'll effectively transform it from an integer variable into a factor. I'm gonna run that. Okay, great. That allows us to use, once more, our great ggplot histograms to visualize the data. So let's take a look and see if we think if there's any interesting signal in sibspa. Before I do that, I'll go ahead and maximize our screen real estate, and then I'll run ggplot. Now, I'm going to zoom in on this because obviously this is not particularly readable given this size. So zoom in, and hopefully that makes it a little bit better. Okay, so to summarize this particular plot, this particular visualization, we're actually looking at 4 things simultaneously, which is pretty cool. We're looking at survival rates, of course. We're looking at the value of sibspa, which is, we can see here 0, 1, 2, 3, 4, 5, 8. So those are our 7 distinct values here that we saw earlier. And then we're saying, oh, by the way, we also want to slice the data by both what class, what passenger class they were in, as well as their title. Because again, we like title. We think title may be predictive, and it seems to be a better fit, hopefully, for us than age. So it's probably something we're going to keep using as an axis in terms of our analysis. We always want to slice by title. Okay, so here we have passenger class first, title of master, miss, mister, so on. Down here we have master, miss, so on. And then lastly we have third class, we have master, miss, mister, and misses. And what we see here is a pretty definitive pattern here of, first and foremost, if you're a master or miss in first class, survival rate, basically you're good to go. From this plot, right? Everything's all turquoise, good. If you're a mister, I'm an adult male, looks like there's no real big pattern. I mean, there's a single value here. It looks like it's kind of an outlier. So I don't think just from this plot alone you can make any strong conclusions. Misses, first, if you're in first class, looks like you survived. If you have the title of other, if you take a close look at the data in Excel or something like that, you'll notice that there's a couple of folks with the title of Reverend, which I'm assuming based on the time in question implies an adult male. You can see here that there's maybe some interesting going on here in a small scale. Again, if you go to second class, master, pretty good, miss, pretty good, mister, oof, yeah. Life's not good. It looks like your survival rate declines the more siblings you're traveling with. Interesting. Misses, also interesting. Could be interesting. Other, not very good. Survival rates. Master in third class. Now that's where this is pretty interesting. What this says is, look, if you're a male child, a boy, you tend to have much better survival rates in third class if you are traveling with a smaller contingent of siblings, because it's unlikely you're married if you're a boy, so we'll infer siblings. And maybe this is the data kind of telling us a scenario, kind of telling us a story, which essentially says, hey, look, all things being equal, if you're a boy and you're in a small family, you're more likely to survive because maybe your parents had better odds of looking out for you. Maybe that's a story or a scenario that could be born of this data. So this is particularly interesting, if you ask me. Miss also seems to bear this out as well, because we already identified that a miss is not married, so therefore the sp portion of the sib-spa variable does not apply. So we can make a logical inference that this is really talking about female children in third class, this siblings only, and this kind of bears out a little bit more of our story that we just told earlier, which is, hey, look, if you're a child, you're more likely to survive if you were with a smaller family unit rather than a larger family unit. This is pretty dramatic here, actually, as you can see this sliding off, even more so than here, right? Good, good, okay, and then basically orange after that. You'll see here misses. This is particularly interesting. This bears out the spouse aspect because the predominant records are 0 or 1, which means either a married woman was traveling without her spouse or without siblings potentially, or with one sibling and one spouse. My guess would be, my intuition would be, this is mainly spouses and not so much siblings. I'm sure there's some sibling records in there, but I bet predominantly this is about spouse. This indicates spouse, whether they're traveling with their husband, essentially. And lastly, Mr. Yep, pretty sad. Look, if you're an adult male traveling in third class, and if you're traveling with a large family. Now remember, the cutoff that we saw is only about 15 or 16, so numbers like this probably aren't hugely out of whack with our intuition, because 15, 16, 17 in the modern US we consider folks adults at 18. Probably in the early 1900s they probably had a bit different aspect on things, so this doesn't shock me per se to see this distribution. To say, look, if you were considered an adult male by English standards, or whoever ran the cruise line that ran the Titanic, and you were traveling with a large family, you were more likely to perish than if you were essentially traveling alone or without siblings or spouses. So that's also interesting. So this is a very interesting plot. Definitely something we want to keep in the back of our mind for future feature engineering work. Similarly, let's take a look at the parent-children variable, or parch. We'll just essentially do the same thing as using the same logic. It's probably very easy to treat this as a factor, so we'll go ahead and convert it to a factor and then do the same type of plot that we just saw. Let's go ahead and run that code. Zoom in on it to make it a little more readable. And here we go. So you'll see here the first thing that you'll notice is that, let's go ahead and go back real quick. Ooh, where did I lost my zoom. Here we go. So you'll notice that on the previous plot that we had more master records. Now if we move to the next one, so you'll notice here that if I use these arrows, not only does it navigate the plot here, it also navigates the plot on the zoom, which is kind of cool. You'll notice that we only have the things shift around, and that's just because of the fact that we're now dealing with parch instead of sib-spa. I'm going to just go ahead and quickly rejigger this. Okay, so we have parch down here, and we can say, okay, yeah, master is either, it's probably looks like all the master folks Again, we're going to assume that a boy does not have any children, so we'll assume this means they're traveling with two parents and they all survived. Miss, mixed bag, as we know, it could be adult unmarried females as well as female children, but they all survived, and typically it didn't really matter whether they were traveling without parents or children, with one parent or child, or with two parents or children. Now, an adult male in first class is where things get interesting. Generally speaking, if they were traveling alone in first class, or excuse me, not traveling alone, traveling without a parent or child, they were more likely to survive than if they would. So if they were traveling with a parent or child, which is interesting. Misses, they all survived. I'm not going to belabor this. Let's just go ahead and jump down to another one that seems to be particularly interesting. Misses. This one's particularly interesting because even though we don't know for sure, we could logically infer that the story here is that these are adult married women, so they're probably predominantly traveling with children because it's unlikely they have 6 parents. And you can see here a very steady decline in survival rates as the number of children go up. So which kind of makes sense, right? Maybe the story here is I'm an adult woman traveling in third class with my children, my family, and the more children I have, because of maybe it's just harder to get everyone together and move through the ship to the lifeboats, or because I can't choose which of my children I want to put on a lifeboat and who don't make me choose between my children. Maybe the story is that the more children you have, the worse off that story is for you, and hence your potential for perishing goes up with the size of your family. Because you'll see here that unmarried women that are traveling with a 0 or 1 parents or children seem to have, or maybe even 2, have far greater survival rates as a class than if you have 6 or 4 or even 5. So that one's particularly interesting. So again, Parch based on title and P-class may be predictive and interesting target for us to do some feature engineering work later on. Okay, so earlier we took a look at it and we said, okay, we'll infer that you're traveling alone if your SIBSPA and your Parch variables are both equal to 0. So we can try a little bit of feature engineering here by creating a family size feature by also using the SIBSPA and Parch variables. So that's what you see here. We've seen this before, but I'll go ahead and pull it up in the help system again. So this is the combine function. And what this says is, okay, great. Grab from the train data frame, which we know over here is 891 observations of 11 variables. Grab all the SIBSPA and grab me all of the SIBSPA from the test, which is 418 observations, and combine them together into one big long vector, or I hate to use the word list because a list is a specific thing inside of R, so maybe I'll say an array. Combine this into one big long array of values and then store it in this variable. Now the reason why I'm doing this instead of grabbing it from the data.combined data frame is because we transform these values from their integer representation into factors. And what I want here is actually their integer representation. Because what I'm going to do is I'm going to add them together to get a total family size feature. And then I'm going to do the same thing for Parch. So I'll go ahead and run those 2 lines of code here real quick. And you can see here I get 2 integer vectors or arrays of 1309, which is great. It's exactly what I want. And now what I can do is I can say, hey, on the data.combined data frame, let's create a new variable called family.size. And I want that as a factor, but I want the values of the factor to be the addition of the SIBSPA count, how many siblings and or spouses am I traveling with, add to that any parents and or children I may be traveling with, and then include myself. And then that gives me the total size of my family. Me as, let's say, an adult male. Am I traveling with any siblings and or my spouse? Am I traveling with my parents or any of my children? And then if you can't, you got to throw myself in there, and that gives you my total family size. Let's go ahead and execute that. Just for grinsies, let's go ahead and click on this over here in the global environment pane, and it'll give us a nice tabular representation. We scroll over to the right. We can see the family size here, and just we can spot check it visually, and we can say, okay, for these two records, these people are traveling with one sibling or spouse, respectively, and including themselves, that gives a family size of 2. This person here is traveling with nobody, so their family size is 1. Okay, so it looks like our logic works. Great. Going back to our handy-dandy histogram, let's plot it in ggplot2 and zoom in on it to see if it's got any interesting aspects to it. Okay, so what this basically says is for passenger class and your title, based on your family size, is there any change in your survivability rates based on your family size in general? And quite a few things that are particularly interesting. You'll notice that there's a lot of stair-stepping, which is kind of what we would expect, right? Generally speaking, even in the early 1900s, large families were more rare than smaller families. And this first bar is basically traveling alone. And you'll see here that you get a nice kind of, in general, you get in a number of instances, a nice kind of gentle sloping off. And in particular, we'll find Mr. is interesting. The bigger the family size, you see a steady kind of decrease in the amount of survival area. Now, whether or not that's significant, we'll have to further explore. You'll see that here as well. Survival rates for Mr. tend to go down in second class as family size grows. For Miss, that seems to be very true in third class. You know, if I'm traveling by myself, I'm far more likely to survive than if I'm traveling with a family size of 11, which is pretty big. Same thing for Mr. in third class, declines. And Mrs. is kind of a mixed bag. So there may be also some predictive power in this family size variable that we just engineered. Okay, so I think that's going to be all for this video. I'm trying to keep these videos down to a reasonable size. I knew the first one was quite long, so I'll go ahead and end here. But before I do so, let's just go ahead and take a quick look at coming attractions, and that's going to be dictated by our data. So what we have left is to take a look at ticketing and passenger fare, cabin, and embarked. And I know this is pretty tedious, but this is the best way that I have learned to build great predictive models and to do data science, which is to spend time with the data. Research and surveys have shown that in the data mining and data science community, on average, you're spending 60 to 80% of your time dealing with data, finding it, understanding it, cleaning it, visualizing it, getting to know it, telling a story, doing some feature engineering. And then the last 20 to 40% of the time, and typically it's closer to 20, not 40, by the way, you are actually building your models and then collating your findings and presenting them to your customers and or the engineering team who may be taking your solution to production. So this is extremely important. It is the heart of data science, is working with the data. And I know that sounds very cheeky, very very intuitive, almost cliche, but it's actually true. So next time we'll tackle the rest of these variables. It should speed up because some of these variables here are, as we'll see, aren't particularly useful from a predictive perspective, as was taking a look at SIBSPA and Parch. These appear to be pretty interesting from a predictive perspective. These other ones probably are not so much. So we'll probably go through faster on the next video. Okay, so that's it for this time. As I said before, the code will be posted up on GitHub. And I look forward to the next video, and hopefully you are finding this useful. Feel free to put comments on YouTube. I do read them and will try and be as accommodating as I can for any feedback that I get. So until next time, happy data sleuthing.